Hi friends, in this video we are going to discuss about concentrated winding and distributed winding. Before this, we should know two terms. One is the phase belt and other one is the phase spread. One is the phase belt and other one is the phase spread. What is that? Phase spread. So what is phase belt? Phase belt nothing but the number of slots per pole per phase. Number of slots per pole per phase. Each number of phase per pole per phase, like that. So number of slots per pole per phase is called phase belt. And phase spread is nothing but the angle made by the phase belt. Angle made by the phase belt is called phase spread. Nothing but phase spread is nothing but m gamma. Gamma into m. Gamma into m is nothing but m gamma. The angle made by the phase belt is called phase spread. In generally, this phase spread is equals to 180 degrees upon number of phases. That is nothing but for three-phase machine, phase spread is equals to 180 of 3. 180 of 3 is nothing but 60 degrees. For two-phase machine, m gamma is equals to 180 upon 2, nothing but 90 degrees, like this. And remember, here for three-phase machine, m gamma is equals to 60 degrees. This is called narrow phase spread. This is called narrow phase spread. I will give you about broad phase spread later. First, remember this. For three-phase machine, m gamma is equals to 60 degrees. This is called narrow phase spread. Okay. This narrow phase spread we can use in single layer winding and double layer winding. In generally we are using this is only narrow phase spread only. Right. So this is about the phase belt and phase spread. Clear? Are you clear? Okay. Let's go for concentrated winding and distributed winding explanation. Which winding is called concentrated winding? Or what is the definition of concentrated winding? Here the name itself indicates that the winding is concentrated. Here the name itself indicates that the winding is distributed. Concentrated, distributed, that is the definition actually. But technically, what is the definition for concentrated winding? Concentrated winding is nothing but in which the phase belt m is equals to 1, that winding is called concentrated winding. In which the phase belt m is greater than 1, that winding is called distributed winding. Nothing but the slots per pole per phase is equals to 1, it is called concentrated. Slots per pole per phase value greater than 1, then it is called distributed winding. This is the concentrated and distributed. That's why we should know the phase belt. Next, in generally we have already concentrated winding. Then again, why we are using distributed winding? Why we are using distributed winding? Here in concentrated winding, EMF is more. Here EMF is less, even though we are using distributed winding. Because Here EMF is more but not a sinusoidal. EMF is less but sinusoidal. This is the reason why we are using distributed winding. Now you have another question. Sir, why it is not a sinusoidal? Why it is not a sinusoidal? Because of higher order harmonics. Because of higher order harmonics, the EMF is not a sinusoidal. Here, higher order harmonics eliminated. Here, higher order harmonics eliminated. That's why here EMF is a sinusoidal. This is very important thing. And also, generally short pitch winding is used for low speed applications. Distributed winding we can use for high speed applications. In transformer we are using concentrated because that speed is 0. For high speed applications, if you use the concentrated winding, it leads to delocation of the winding from the slots. It is delocated from the slots for high speeds. That's why for high speeds we are using distributed winding. I will give you clarity, just wait. I will give one example for these two windings, then you can get 100% clarity. Okay? Right, listen. So this is generally about the concentrated and distributed winding. Now, what is next? Example. Let's take the example for each and every winding. Right. See the example for concentrated winding and the example for distributed winding. Example for concentrated winding and distributed winding. How we are going to discuss, see here. I said you already, M is equals to 1. M should be greater than 1. Take the example. Example, a 3-phase, 4-pole, 12 slots alternator. Let's check is this is the concentrated or distributed. See how many poles are there? 4. How many slots? 12. How many slots per pole? Slots per pole nothing but 12 of 4, nothing but 3. Slots per pole 3. What is the slot angle? Slot angle gamma is equals to 180 upon slots per pole, nothing but 60 degrees. Are you okay? Getting bored or sleep? Listen carefully. Here, phase belt is equals to, phase belt M is equals to slots per pole per phase, nothing but slots per pole 3, and this is a 3-phase machine. 3 out of 3, nothing but 1. If M is equals to 1, then the winding is called concentrated winding. Let's see here. I have a 4 poles. And number of slots for each phase is, number of slots for each pole is 3. Here 3 slots are there for each pole. Slots per pole 3, but slots per pole per phase. I want per phase. Actually, this is a 3-phase machine, nothing but R phase, Y phase, B phase. These are the 3 phases. And here, in each pole, I have only 3 slots, nothing but this belongs to R phase, this belongs to Y phase, this belongs to B phase. For R phase, I have only 1 slot. For Y phase, I have only 1 slot. For B phase, I have only 1 slot. Nothing but M is equals to 1. That's why it is called concentrated winding. This is about concentrated winding. about distributed winding. I am taking the same question. I am taking the same question. 3-phase, 4-pole, 36 slots alternator. 36 slots alternator. Is it okay? 36 slots alternator. See here, again, number of poles are 4. Number of slots are 36. Slots per pole, 9. And the slot angle, gamma is equals to 20 degrees, 180 by 9. And phase belt M is equals to slots per pole per phase, 9 out of, how many phases are there? See here. Is it okay or not? 3. 9 by 3 is equals to 3, which is greater than 1. So here M is greater than 1, that's why it is distributed winding. How many poles are there here? 4 poles are there. How many slots for each pole? For each pole, I have 9 slots. And here per phase, how many phases are there? 3 phases. Nothing but R phase, Y phase, B phase. 3 phases are there. Tell me, for 3-phase machine, how many slots for each phase? Total 9 slots are there in my pole. These 3 belongs to R phase, these 3 belongs to Y phase, and these 3 belongs to B phase. Nothing but my phase belt is 3. My phase belt is 1. My phase belt is 1. My phase belt is 3. This is simply distributed. Still you are not getting clarity, right? Listen 1 minute, you can get the clarity about concentrated and distributed carefully. For example, in my machine, I have 150 slots. In my machine, I have 150 slots. 150 slots, nothing but 50 slots for each phase. 50 slots for R phase, 50 slots for B phase, 50 slots for Y phase. Or, for example, in my machine, I have around 300 slots. Nothing but 300 slots, nothing but R phase 100, Y phase 100, and B phase 100. Or in my machine, I have 900 slots. 900 slots, nothing but for R phase 300, for Y phase 300, and for B phase 300, like this. This R phase 300 slots, R phase 300, this is, for example, number of conductors, for example. 900 conductors or 900 tons. Whatever. For example, 900 conductors. In that 900 conductors, R phase having 300 conductors, Y phase having 300 conductors, B phase having 300 conductors. This R phase having 300 conductors, that 300 conductors placed in one slot. This 300 conductors of Y phase placed in one slot. This 300 conductors of B phase placed in one slot. Nothing but the total conductors are concentrated. The total winding is concentrated in one slot. This 300 conductors placed in only one slot of R phase. Nothing but this 300 conductors here only. In this slot, I have 300 conductors. The total number of conductors are concentrated. But here, R phase having 300 conductors, but this 300 conductors not concentrated. This 300 conductors are distributed each 100 conductors. In this slot 100 conductors, in this slot 100 conductors, in this slot 100 conductors. Here, the 300 conductors are distributed for 3 slots. Here, these 300 conductors are concentrated in one slot. Here, the concentrated, here, the distributed. This is simply what is concentrated and distributed winding. Now tell me, in which the speed is maximum level? If here the speed is maximum, here only in one slot 300 conductors. At higher speeds, some conductors may delocate. But here, in one slot, we have just 100 conductors. So, even though the speed is higher, no problem. Because here 300 are there, but here only 100 for each slot. This is easy to rotate at higher speeds. That's why distributed winding is used for higher speed and concentrated winding is used for low speed. If at higher speed, if you are using concentrated winding, some conductors may delocate from the slots because of more number of conductors in one slot, because it is a concentrated type of winding. It is distributed to many number of slots. This is what the concentrated and distributed winding. Are you okay? Getting or not? So up to this, I given you the difference between concentrated and distributed and an example. Right? Now, what is our aim? We have to eliminate the harmonics. How we can eliminate the harmonics? Right? Let's see about that. For example, I have m number of slots. For example, the slots are like this in these windings. This is one slot and this is second slot. Sir, what is the angle between these two? The angle between these two is gamma, the slot angle. And actually it should be like this, but the next slot is differentiated with phase shift of gamma. Like this, it is going on. If these slots, the more number of slots are there, then it comes as a circle. Then it comes as a circle, pure circle. If the diagram is pure circle, then EMF waveform is pure sinusoidal. If diagram is pure circle, EMF waveform is pure sinusoidal. If more, I have just 3 number of slots here. If I have 30 number of slots, then next one, it is a pure circle. Nothing but if more number of slots are there, if m is equals to more, then we can get the circle, then the EMF waveform is perfectly sinusoidal wave. Okay? Right. So, for example, if the center of the circle, I have a circle, the center of the circle is like this. Okay? So, these are the radius of my circle. These are the radius of my circle. Radius of my circle. This is the radius R. Radius of my circle. Of course, if this is gamma, this angle also gamma, this angle also gamma, this angle also gamma. Like that, we have a m number of slots, then the total angle is m gamma. We have m number 1, 2, 3, like that m. Nothing but the total angle is m gamma is the total angle. Right. For example, here the EMF induced in this slot E, and EMF induced in this slot also E, and the EMF induced in this slot also E, like that. Like that, we have m number of slots. Here we have to calculate EMF induced in concentrated and distributed winding. In concentrated, arithmetic sum or vector sum? Very good arithmetic sum in concentrated, and in distributed vector sum. Right? Let's see here. I am going to derive the EMF resultant values. For that, I am doing some modifications here. Listen carefully. This is very important. So see here, I am doing perpendicular line for this EMF or this angle, both. So when I am doing a perpendicular line, this is the a perpendicular line. Nothing but now this EMF is E by 2 and this EMF is E by 2 because of perpendicular 50-50. And here the angle is 90 degrees. Here the angle is 90 degrees. And listen carefully, if this total is gamma, now this angle is gamma by 2 and this angle also gamma by 2. Both are gamma by 2. This is point O, this is point A, this is point B, this is point C, this is point D, O, A, B, C, D, and for example, this is a point I am taking as a P, point P. Now, take this triangle, O, P, A triangle. Can you tell me what is this value? This value is E by 2. And this value is R. We don't know this value. No need of that. And this angle is gamma by 2. This angle is gamma by 2. I want the EMF. Nothing but the opposite angle. I want the opposite side. Opposite side, nothing but which belongs to sine theta or cos theta. Tell me. Very good. Sine theta. So tell me, what is sine theta? Sine theta is nothing but opposite side upon hypotenuse. What is opposite? E by 2 upon R. From this I want E. Tell me, sir, what is E? E is equals to 2R sine gamma by 2. 2R sine gamma by 2. E is equals to 2R sine gamma by 2. This is the EMF in one slot. But we have a m number of slots. That too, for example, concentrated winding, I am taking concentrated winding. In concentrated winding, arithmetic sum. Arithmetic sum, one slot EMF is this much. For m slots, EMF is, for example, one slot 10 volts. One slot. For 3 slots, 10, 10, 10. What is the arithmetic sum? 30. Like that, for one slot, here E is equals to 2R sine gamma by 2. For m slot, the EMF induced, the arithmetic sum of EMF induced in concentrated winding is equals to multiplied by m. So the answer is 2Rm sine gamma by 2. 2Rm sine gamma by 2. This is EMF induced in concentrated winding. Are you okay? Now let's go for distributed winding. But this is not a arithmetic sum, this is a vector sum. How we can get the vector sum? These are the 3 vectors. This is the resultant vector. This is the resultant vector, the EMF of distributed winding. Are you okay? So now we have to find out the EMF of distributed winding, how much. For this, take the property of similar triangle. What is that? Similar triangle property. First, take the triangle OAB. Take the triangle OAB. What is the triangle OAB? OAB is like this. Actually, OAB is like this. This is R and this is also R. And this is the EMF E. And this is the angle gamma. See? OAB. Angle is the gamma. And EMF is the E. And these are the 2 radius R. From this, can you tell me what is E? Actually, we calculated here. What is E? E is equals to 2R sine gamma by 2. Observe clearly. 2r. Because of radius is r, so it is 2r. Here the angle is gamma, here sine gamma by 2. Similarly, take the triangle OAD triangle. Take the triangle OAD. So take it. This is OAD. This is OAB, right? But this is OAD. This is the EMF of the distributed winding. This is radius R, this is radius R. Can you tell me what is this angle? M times of gamma, nothing but M gamma. Are you okay getting or not? Now tell me, sir, what is EMF? What is EMF developed in distributed winding? What is EMF developed in distributed winding? Similar triangle principle. Here R is there, here R is there, here 2R is there. 2R. Here gamma is there, so the answer is sine gamma by 2. But here M gamma is there, so the answer is sine M gamma by 2. Sine M gamma by 2. This is EDW. So what is the EMF developed in distributed winding? The vector sum is 2R sine M gamma by 2. This is the EMF developed in distributed winding, and this is the EMF developed in concentrated winding. This is the arithmetic sum, and this is the vectorical sum. So we calculated these two formulas are important. Getting or not? Now the next. Tell me what is next? Very good, KD. What is next? KD. What is KD? Distribution factor. Very good. Still? Yeah, very good. Phase belt factor. Phase spread factor. So let's go for distributed winding concept, that is KD. So let's go for KD. Distribution factor, phase belt factor, phase spread factor. Very important for our examination. Based on that KD, they may ask you question in our examination. Listen carefully. I'm taking KD, nothing but distribution factor or phase belt factor or phase spread factor. Phase spread factor. Let's discuss about this. Tell me, what is the definition of KD? This is similar to KP. Yeah, tell me fast. Very good. What is that? The vector sum of EMF induced in distributed winding upon arithmetic sum of EMF induced in concentrated winding. Vector sum of EMF induced in distributed winding upon arithmetic sum of EMF induced in concentrated winding. This is simply the KD. So KD is equals to, what is EMF induced in distributed winding? 2R sine M gamma by 2 upon, what is concentrated winding? 2R M sine gamma by 2. 2R gets cancelled. So the KD, what is distribution factor, is equals to sine M gamma by 2 upon M into sine gamma by 2. This is the distribution factor KD. Is it okay? Right? Very important one. Now this is simply KD. Can you tell me what is KD3? what is KD phi, and what is KDN. Finally, I want KDN. Nth component of distribution factor. Nth component of distribution factor is equals to sine n m gamma by 2. Is it okay? Clear or not? Is it okay or not? Sine n into m gamma by 2 by m into sine n gamma by 2. This is what KD of nth factor. Here we have to eliminate the harmonics, right? How we can eliminate the harmonics? How we can eliminate the harmonics? Yes, by equals to 0. We done already in KP. So tell me, if KDN is equals to 0, nothing but sine n m gamma by 2 upon m into sine n gamma by 2 is equals to 0. If bring this is also 0. So what is the answer? Sine n m gamma by 2 is equals to 0. 0 can be written as in terms of sine 180. Sine theta is equal to sine theta. So theta is equals to theta again. Theta is equals to theta. So tell me, what is m gamma from this? M gamma is equals to 360 degrees by n. Here n is not number of phases. Yeah, very good. N is order of harmonics. Order of harmonics. This is what m gamma. M gamma is equals to 360 degrees by n. Then n is the order of harmonics. For example, they will ask you question to eliminate third order harmonics. To eliminate third order harmonics. Third order harmonics. M gamma is equals to 360 upon third order, that is equals to 120 degrees. That is equals to 120 degrees. To eliminate third order harmonics, m gamma is equals to 120 degrees. Like that. To eliminate ninth order, 360 degrees by 9, 40 degrees. Like that, they may ask you questions on distributed winding. Is it okay? Clear? Right? Right. Now the concept is completed. Now one question. What is KD for concentrated winding? What is KD for distributed winding? Tell me the answer first. First I want KD for concentrated winding. Yeah, very good answer. Good answer. I want KD for concentrated winding. Let's see here. What is distribution factor for concentrated winding? For concentrated winding, m is equals to 1. What is actually KD? KD is equals to sine m gamma by 2 upon m into sine gamma by 2, right? But for concentrated winding, m is equals to 1. Substitute m is equals to 1. So KD for concentrated winding is equals to sine gamma by 2, because m is equal to 1. M is equal to 1. Sine gamma by 2 gets cancelled, is equals to 1. So KD for concentrated winding is equals to 1. Is equals to 1. For distributed winding, KD value less than 1. For distributed, KD value less than 1. As usually, KD1 is greater than, KD3 is greater than KD5. As usually, this is everything is same like a KP. Is it okay? Understanding or not? Right. Now you have a one doubt. What is the doubt? What is the doubt? Let's see here. I will explain what is your doubt and what is answer. For three-phase machine, m gamma is equals to 180 by 3, that is equals to 60 degrees. To eliminate the third order harmonics, m gamma is equals to 360 by 3, 120 degrees. Actually here, the formula is m gamma is equals to 180 degrees by phases, but here m gamma is equals to 360 degrees by order of harmonics. These two are very different, not same. Okay. And I said you, when m gamma is equals to 60 degrees, that is narrow phase spread. But when m gamma is equal to 120 degrees, that is called broad phase spread. Okay, broad phase spread and narrow phase spread. Generally used for three-phase machine. This is rarely used for three-phase machine. This is generally used for three-phase machine. But here it contains third order harmonics. It contains third order harmonics in phases. Generally third order harmonics are zero in line. Remember this point. Third order harmonics are eliminated in line. But here it contains third order harmonics in phase to phase. But here third order harmonics eliminated. Third order harmonics eliminated in phase and line. In phase and line. In both the cases third order harmonics eliminated, but here third order harmonics contains in phase. Here EMF is not sinusoidal. But here EMF sinusoidal. Is it okay? Are you okay? Generally this is used for single layer winding and double layer winding, but this is used for double layer windings. This is used for single layer and double layer. Here third order harmonics are there in phase, so EMF not sinusoidal. Here EMF is a sinusoidal because third order harmonics eliminated in phase and line. And here narrow phase spread, generally used for three-phase machine, rarely used for three-phase machine. M gamma 360 by n, m gamma 180 by number of phases. If it is 60 degrees narrow, if it is 120 degrees broad. This is completely what is concentrated and distributed winding. Right? Okay. Finally, one question. You have to give me the answer. Listen carefully. You have to give me the answer. Option A, short pitch concentrated. Option B, short pitch distributed. Option C, full pitch concentrated. Option D, full pitch distributed. In which of the following case we can get sinusoidal EMF? In which of the following case we can get sinusoidal EMF? Tell me the answer. In concentrated, EMF is not sinusoidal. Yes or no? In full pitch, EMF is not sinusoidal. Then when we can get the sinusoidal? Short pitch and distributed winding. We can get the sinusoidal EMF because here lower order harmonics eliminated and here higher order harmonics eliminated. Here alpha is equals to 180 by n. Here m gamma is equals to 360 by n. This is the concept. So finally, you know what is Kp, pitch factor, what is Kd, distribution factor, but I want winding factor. Winding factor. Windings, these two are the windings. Winding factor Kw is equals to Kp and Kd. Kp multiplied with Kd. Winding factor is equal to Kp multiplied with Kd for full pitch concentrated winding. For full pitch Kp1, for concentrated Kd1, for full pitch concentrated, winding factor is equals to 1. This is the concept of full pitch, short pitch, concentrated, distributed. Understood? Okay? Right. Thank you.